So I said the direct comparison test doesn't always work because you have to have the inequality facing a certain way. And so there's this other version of the comparison test, which is called the limit comparison test. And you don't need an inequality for this at all. So let's say, again, you have to have series that have positive terms. So your original one, a sub n, and your new one that you're comparing it with, b sub n, need to be series with positive terms. The name of this test says limit, so you're going to have to compute a limit here. So if the limit of a sub n over b sub n is c, where c is a finite number, and you need c to be strictly bigger than 0, then either both series converge or both diverge. So limit comparison test, what it's telling me, I have two series with positive terms. If I take the limit of the ratio of their terms and I get a finite number that's not 0, these two series have to behave in the same way. They both have to converge or they both have to diverge. They have to agree with each other in some way. Okay? All right, so let's do an example of a place where I would use the limit comparison test. Test the series. It's going to be n equals 1 to infinity, 1 over 2 to the n minus 1 for convergence or divergence. So anytime you want to use a comparison test, you start by asking yourself, do you have positive terms here? Do I have positive terms here? Numerator's positive, the denominator's positive, so I'm good to go on using a comparison test. So from this one, remember I want to make a slight change.
So we compare it to 1 over 2.
Yep, exactly. This is what I'm going to do, is I'm going to take away that minus 1 over 2 to the n. That was my slight change I made. These both have positive terms. So let's just try to use the direct comparison test here like we did on the previous problems, okay? So I have these two terms, 1 over 2 to the n minus 1, 1 over 2 to the n. Which one is bigger? Hold on. It's 1 over... Which one has the larger? Because I'm subtracting by 1, so that means the denominator on the left is smaller, and a smaller number means I have a bigger number, right? Right? If you're unsure, let me explain how you can figure that out. So this is kind of like I did before. If you're unsure, just leave this as a question mark and fill it in. If I cross multiply, I get 2 to the n over here and 2 to the n minus 1. Which one of those numbers is larger? 2 2 to the n. Because the other one, I've subtracted it by 1. So I can go in now and fill in my question mark. I know which one is larger. It's this one on the left. Okay, so now I know how they compare. I got to look at my comparison one, which was this 1 over 2 to the n. And I need to see, does this series converge or diverge? What kind of series is that? Maybe it'll help us.
P-series or not P-series?
Not, because remember, for a p-series, the power needs to be fixed, right?
Geometric.
It's geometric. If we write out some of the terms, do you see? It's 1/2, 1/4, 1/8, and so forth. That's a geometric series. So this is geometric. What's my R value? 1/2. For a geometric series to converge, the absolute value of R needs to be less than 1, and it is. So here, this series converges. But if you look at the inequality, what I have now is something smaller converges. That doesn't tell me that my bigger thing, the 1 over 2 to the n minus 1, that doesn't tell me that it converges. So I've got this problem that this inequality is not facing the right direction. I need it to be flipped the other way in order to make a conclusion here. Okay, so because of that, the direct comparison test is inconclusive. Inconclusive.
Can you repeat that part one more time?
Yeah. Okay. We've just said that this series 1 over 2 to the n, it converges, right? So what we do is we go back up to the way our inequality pointed. If, what I said is now, if you look, this 1 over 2 to the n was smaller, right?
Oh, yeah.
The smaller thing converging doesn't tell me that the bigger thing converges. The bigger thing could still diverge.
I see what you're going to do.
Yeah, if you look back at our statement of our direct comparison test, if our B sub n converges, right, what does our inequality need to look like? B,
It's less than
yeah, but I don't have that. A sub n is bigger than B sub n.
Yeah.
What I have here says that, let me write it in red. A sub n is bigger than B sub n. And this said that B sub n converges. So if you look at the line in the direct comparison test, when B sub n converges, A sub n needs to be less than or equal to B sub n, but I don't have that.
So the test fails.
So the test fails, yep. But the test failed, but we have this limit comparison test that we can do instead, okay? So let's do the limit comparison test. So my terms, just to remind us, A sub n was what I started with. It was 1 over 2 to the n minus 1. And B sub n is 1 over 2 to the n. So if I'm using the limit comparison test, I need to compute the limit of A sub n divided by B sub n. The limit of 1 over 2 to the n minus 1 over 1 over 2 to the n. So I'm going to flip the bottom fraction up to simplify it, so I get 2 to the n over 2 to the n minus 1. What I'm going to do here is I'm going to multiply top and bottom of my limit by 1 over 2 to the n. So all I did was multiply by 1 here. And what that's going to do is that's going to give me 1 for the numerator. And I've got to distribute that to the terms in the denominator, 1 minus 1 over 2 to the n. Okay. And now what do I get for that limit? The numerator is 1. The denominator, I get 1 minus 1 over 2 to the n. That's going to give me 0. So I'm just getting 1 for the limit. With the limit comparison test, all you care about is that you get a finite number that's not 0. So I got a finite number that's not 0. So both of these series, the one we started with and the one we're comparing it with, they have to behave the same way. They both have to converge or both have to diverge. But didn't we say that one of them converged? Yeah. We said up here this one converged, right? 1 over 2 to the n. So that means since they both have to do the same thing, mine has to converge as well. Okay? So come down here.
So if this were to equal 0, would we have to do some other test?
Yep, exactly. Yep.
Here makes it equal.
Yeah, if you get 0 or infinity, you have to use some other test, or maybe you should compare it to a different series. Yes.
Okay, how did you get 1 over 2 to the n when you multiplied them?
Multiply the top numerator.
So in the top, I multiply and I get 1, right, because they cancel. And then in the bottom, I've got to distribute this. So when I multiply the first one, I get 1, and the second one, I get minus 1 over 2 to the n. Yeah. Okay. Yep.
So does that mean you always have to do both tests? So,
You don't have to do both tests.
well, I mean, if like the first one.
If the first one doesn't work, then you could do the second one. And see if it works. Yeah. Sometimes I'll just start, depending upon what's there, I might just start with the limit comparison test and just compute a limit. I just wanted to show you that there are some cases where the direct comparison test doesn't work.
Okay.
Yeah.
Well, because I saw that you compared like since the last one compared.
Yes, exactly. So I haven't stated my conclusion yet, so I should do that.
What
So
happens if you got this one converge, would you still do the other test to compare it, or?
if I got that, hold on, what is your question? If,
Because you got that this converge because it's kind of the same as the other one. It can all converge. So like, if you just did the limit test instead of converge, what would you compare it to? Or you just say converge?
to do the limit test, you have to compare it to something to begin with.
Okay.
So you'd still have to pick, it's still the same kind of initial steps as the direct comparison test. You start with your series, you create a new one, and instead of doing the inequality, figuring out which one is larger, you would just jump to doing a limit.
Okay.
Okay?
So we should see if that one fails first, and if that fails, then we go to this one. The comparison.
You can, yeah, or sometimes I'll just go, like, if I know I can calculate the limit pretty easy, I might just already start with the limit comparison test instead. We'll see one, I'll show you one in just a minute where I'm gonna do the limit comparison before the direct, yeah.
So we have done the other examples with this already.
With the limit comparison,
Yeah.
you could for, hold on. You could for the first one, yes. For the second one, I think if you compute that limit, you would have got infinity for that limit. So it wouldn't have worked, but you can try it, yeah. And if you get a finite number that's not 0, then you're good. Okay. All right. So my original series, which was what? It was n equals 1 to infinity, 1 over 2 to the n minus 1, converges by the limit comparison test.
Can you shorten it to just LCT?
Yep, LCT.
If we did that in an exam where we just shorten it, would you?
That's fine. As long as you're using the same like acronyms, I know what you're talking about. You're not making up some other name, then that's fine, yeah.
Take it because we use limits.
Yeah, it's an L because you're taking a limit, exactly.